Hello guys, today we're doing A-level chemistry, atomic structure and the periodic table, which is Edexcel topic 1. So for the first subunit, we've got protons, neutrons and electrons, and I've written some summary questions here. If you can answer all of them correctly, then move on, but if you can't, then stay on this topic, and you can pause it and read it if you want to. So we've got the structure of an atom here, we've got protons and neutrons in the nucleus and electrons in the shells. So inside an atom is the nucleus, which is very small compared to the atom, and it makes up most of the mass of the atom. A tiny amount of the mass is made up of the electrons. So protons are subatomic particles with an AMU, atomic mass unit, of about 1, and a relative charge of 1 plus. Neutrons also have an AMU of about 1 and a relative charge of 0. They're very slightly heavier than protons by a tiny amount, which you don't need to know. Electrons are a subatomic particle with a charge 1 minus. They're found in all atoms, and they have an AMU of 1 over 1835. They're found arranged in shells around the nucleus, and these shells are an area where they're most likely to be. They're they're not a set they're not at a set distance from the nucleus. They can move a little bit, and it's just where they probably are, because we can't measure where they are exactly, but the shells tell us where they're likely to be. Electron shells are also divided into subshells, which we will learn about later. The formula for the maximum number of electrons in a shell, n being the principal quantum number, is 2n squared. The principal quantum number is just the number assigned to the shell. So the first shell would have n be 1, and the second shell n would be 2, and so on. So now we've got the history of the atom. The atoms were first theorized by Democritus around 2,500 years ago, but they couldn't prove atoms because it was ancient Greece, they didn't have the equipment. In 1808, Dalton theorized that all elements are made of indivisible atoms, and all atoms of an element have the same mass and are identical to each other. We now know that that's wrong because of isotopes, and also because atoms can decay. And in 1897, Thomson showed that a beam of rays could be deflected by an electric field going towards the positive side. So that proved the existence of electrons, because that's the negative particles. And it also showed that they're a lot lighter than atoms, so there are components smaller than atoms, proving Dalton wrong. And then in 1904, he published his plum pudding model. A little bit more recently, there was the Geiger-Martin experiment, which we learned about in GCSE Chemistry. And the results of this experiment showed that the atoms are mostly empty space. They've got a tiny positive nucleus, and the positive charge is due to protons, which are a lot heavier than electrons, and the electrons are surrounding the nucleus and shells. In 1932, they were wondering why the mass of helium is 4 times the mass of hydrogen, even though it's only got 1 more proton. So that's when Chadwick decided to fire alpha particles at a target, and that released some radiation showing that there were massive uncharged particles, which were neutrons, and that explained the mass of helium compared to hydrogen. So here's the summary questions. So question 1, what is the AMU of an electron? 0.0005, or 1 over 1835, if you want that precision. So question 2, what's the maximum amount of electrons in each shell? Give at least the first 3 shells. It's 2, then 8, then 18, then 32, and then if you did any more, then you just use the formula 2n squared. Question 3, which subatomic particles are found in an atom and where are they located? So there's protons in the nucleus, neutrons in the nucleus, and electrons in the shells that surround the nucleus. And 4, what are the masses and charges of these particles? The mass of a neutron is 1 relative mass, and the charge is 1 plus. Mass of a neutron is 1, and the charge is 0, and the electron is 0.0005, and the charge is 1 minus. So now on to topic 2 and 3, isotopes and relative masses. So first we've got mass number and atomic number. The mass number is number of neutrons plus number of protons. Right, now we're on to mass number and atomic number. The mass number of an atom is the number of neutrons plus the number of protons, that's in AMU. Relative atomic and molecular mass is measured in atomic mass units. The 1 AMU is relative to 1/12 of the mass of an atom of carbon-12. That's how it's standardized. The atomic number is the number of protons in an element, and this number is the same for all isotopes and variations of that element, because obviously changing the number of protons would change which element it is. For example, all atoms with 6 protons are carbon atoms, because that's what a carbon atom is. An isotopes are atoms of the same element with different numbers of neutrons, or different atomic masses. And mass number takes isotopes and relative abundance into account. So it takes the average of the masses of different isotopes. So it just takes into account all of the atoms of that element and averages it out. Molecular mass also takes this into account. Isotopes are chemically quite similar to each other because they have the same electronic configuration, so why wouldn't they be similar? Except the radioactive ones are not. So the isotopic mass is different from the relative atomic mass, because isotopic mass is the mass of a specific isotope, and it doesn't take into account the other isotopes. So do not use average mass in this definition, because you'll lose a lot of marks for that. Well, you won't lose a lot of marks, but you'll lose 1 mark, which is significant. And that is, of course, relative to a 12th of the atom of carbon-12. Atomic mass is where you use average mass of an atom, taking into account all isotopes of that element and the amount of that isotope, the relative abundance. For example, chlorine has 2 stable isotopes, chlorine-35 and chlorine-37. 75% of chlorine atoms are of the chlorine-35 isotope, or 25% are chlorine-37. So the average is 35.5 because you use a little formula. 75% times 35 plus 25% times 37 equals 35.5. It's not much of a formula, but it's very important. You've got to remember that. I've got the formula down here. Atomic mass, relative atomic mass, is percentage 1 times isotopic mass 1 plus percentage 2 times isotopic mass 2, and you've got more than 2, and that just continues. Summary questions. 1. What are isotopes? Atoms of the same element with different amounts of neutrons or different mass numbers. 2. What's the difference between relative isotopic mass and relative atomic mass? Relative isotopic mass refers to the mass of an isotope of an atom, and relative atomic mass refers to the average mass of an atom, taking into account its isotopes and their relative abundance, or their amount. Define relative molecular mass. It's the average mass of a molecule relative to the mass of a 12th of an atom of carbon-12, because it takes into account the so mass spectrometry. So we're introducing mass spectrometry, which is used to accurately determine the mass of atoms and molecules, because you can't directly measure the mass of an atom, it's too small in it. So a mass spectrum, that should be, is a graph of relative abundance against mass to charge, which is usually just the mass. We'll look into that later. This is because during ionization, 1 electron is knocked off the outer shell to form a 1 plus ion, so mass over charge is just mass over 1 usually. So first we've got preparation. I've got a nice diagram here from Wikipedia. Before we start the mass spectrometry, the sample has to be vaporized so that it can be ionized, because obviously if you don't vaporize it, you can't ionize it because there's still things in between, you can't access the electron shells. The mass spectrometer must also be in a vacuum, otherwise the air molecules would deflect the sample. Since it's all gas, they will be knocking each other around, wouldn't be able to get through, would they? And they could also be picked up by the detector. So stage 1, ionization. So you've got 2 options here. The first option, which is the one we're learning about, is electron impact ionization, where an electron gun is used to fire electrons at the gaseous molecules, and it knocks an electron off the outer shell and forms a 1 plus ion. See why it has to be gas now, because you can't do that with a solid or a liquid. And the second option is electrospray ionization, which is where they apply a voltage so that every gaseous molecule gains an H plus ion. This is used for molecules that will be fragmented from electron impact ionization, such as DNA and other polymers. Got to keep them together. The stage 2 is acceleration, where an electric field makes the ions start moving towards the negative side because they're positive. And all ions will have the same kinetic energy, and they will go down the mass spectrometer. It's very important that they all have the same kinetic energy. We'll learn about that later. And since the ions are positively charged, they'll go to a negatively charged plate, and the potential energy from the voltage will become their kinetic energy. So in deflection, I've handily circled this here. So there's a magnet here, you see that, and the negative pole of the magnet will attract the ions towards it, so that deflects their path, making them go all curved. And the ions will take slightly different paths based on their masses. Heavier ions will be less deflected, and lighter ones will be more deflected. That's because it's a lot easier to move a light object than a heavy one. And then there's a nice little formula that you should have learned. Kinetic energy equals a half mv squared, where m is mass and v is velocity. Then the ions drift towards the detector plate where they're detected, And since they all have the same kinetic energy, the lighter ions will drift faster and they'll be detected first, so then you can know their masses. And after that, you've got detection where the ions are separated into mass because of their speeds, and they hit a negatively charged plate, which generates a current, and then the size of the current is like picked up by a little computer. It shows how many ions have hit it for a particular mass, giving us the mass to charge as well as the relative abundance from how many ions. And then they generate a mass spectrum, which is the graph over here. So now we're learning how to read the mass spectrum. The graph is plotted abundance against mass over charge, and abundance will be either in a percentage or in a ratio, which it seems to be here even though it says percentage. And it will be a ratio of the molecule and its fragments against each other, so they're all against each other here. And M over Z, mass per charge, will usually be mass over 1 because the charge is 1 because 1 electron knocked off. But in some rare cases, it can be mass over 2 or mass over 3 if more than 1 electron gets knocked off, but that's rare. The number of ion peaks, which is the lines, every line is an ion peak, tells you the different number of isotopes, the number of different isotopes or molecules being shown. Lines with a significantly lower mass per charge show you fragments of a molecule, then the big line will be the actual molecule. So I've got a nice mass spectrum here. So what does this mass spectrum tell you about bromine? Look at the mass, the fragmentation, and the relative abundance. So you can see that there's 2 isotopes of bromine because of these 2 peaks here, quite low down. And since bromine is diatomic, it will form a molecule. So these down here are the fragments. And it will give a mass of 158, shown here, 160, shown here, and 162 over here. And this is like basic probability trees. Like you did probability trees in math, so it will be like 79, and then it could be 79 again, or it could be 81. And then down here, 81, and it could be 79, could be 81 again. Because of that probabilities, that means that the middle one is twice as likely as these little ones down here. And the relative abundance here is a ratio rather than a percentage, otherwise it would be like more than 200%, you can't have that. So you have to equate the values here, so that the ratios add to 1. And here it's simple because the isotopes are equal. They're 30 to 30 is the values there, which is 0.5 to 0.5. Then multiply 0.5 by 79, and then add that to 0.5 by 81 to get the relative atomic mass. So now more details on how to work it out. Given percentages, it's nice and easy. You just multiply each percentage by its corresponding isotopic mass, and then you add it all together. Given ratios, you've got to simplify it until they all add up to 1, so that it's percentage form. And then you can do the same thing you do with percentages. And sometimes you'll get a slightly more complicated question where you're given the relative atomic mass, and you've got to find the percentage abundances. So I've done an example for you. I think you get one of these questions in the summary questions. So if an atom has a mass of 60.8 and its isotopes of masses of 59 and 61, find the abundances. So you want to find the percentages. So I've got percentage 1 as x, and percentage 2 as 1 minus x, because percentages add to 1, so it must be 1 minus x. So that equals to 60.8. 59x plus 61 minus 61x equals 61 minus 2x equals 60.8. Thus 2x equals 0.2. That's just to find x. And that means x equals 0.1, which is 10%. And, well, now we have 1 minus x. 1 minus 0.1 is 0.9, which is 90%. So now we have our relative abundances. That's that question done. Now onto the summary questions. 1. Why must mass spectrometry take place in a vacuum? Because the air molecules would deflect the gaseous ions, or they could be detected. And 2, an atom has 2 isotopes, 30% have a mass of 30, and 70% have a mass of 35. What's the relative atomic mass? Might well calculate for that one. 0.3 times 30 plus 0.7 times 35 is 33.5. 3. An object is travelling at a velocity of 0.5 meters per second, and it has a kinetic energy of 1 joule. Calculate the mass in kilograms. It's a nice easy one. 2 times 1 over 0.5 squared is 8 kilograms. That's the formula half mv squared. And 4, where will the ion peaks on chlorine be, and what will their relative abundances be in ratios to each other? That's a slightly more complicated one, but there will be a peak at 35 and at 37, because that's the isotopes. You see that there's more 35 than 37, and there will be a ratio of 3 to 1. And there'll also be peaks at 70, at 72, and at 74, with ratios of 9 to 6 to 1, as with our probability tree. The possible molecules are both with 0.75 times 0.75, because that's the probability of getting a 35, or with 0.75 times 0.25 plus 0.75 times 0.25, because that's the probability of a 35 and a 37, or 0.25 times 0.25, because that's the probability of two 37s. That's how you get that ratio. So now on to the next topic, ionization energy. This is a nice topic. So first, ionization energy. Ionization, as we've seen in mass spec, is knocking an electron off of an outer shell to add 1 plus to its charge. First ionization energy is the energy required to knock off 1 electron from every atom of 1 mole of atoms, forming 1 mole of 1 plus atoms. And these must be in the gas state, because then there's little attraction between other particles, and that would affect the ionization energy. So we want as little factors as possible here. So that's the formula. M in the gaseous state creates M plus, also in gaseous state, plus E minus. And then there's successive ionization energies like second, third, fourth. Second ionization energy is the energy required to knock off 1 electron from 1 mole of 1 plus ions to form 1 mole of 2 plus ions. So M plus forms M2 plus E minus. And then the third ionization energy is like the same, but M2 plus forms M3 plus E minus. And the nth ionization energy is M minus 1 plus creates M n plus E minus. It's very simple. Factors affecting ionization energy. So it's based on the attraction between the electron and the nucleus. More attraction means it's harder to take off, so that makes it higher ionization energy. The attraction between them is based on nuclear charge, atomic radius, and shielding, which I'm about to explain. Nuclear charge is the charge of the nucleus, which is the proton number, because protons got charge of +1. So electrons are attracted to the positive nucleus because opposite charges. When there are more protons, the nuclear charge becomes higher, which increases the attraction of the electron to the nucleus, so they get held closer to the nucleus, making it harder to remove an electron from outer shell, which is given a higher ionization energy. This trend is seen across periods because that's when the proton number increases. Now onto how atomic radius affects it. The atomic radius is the distance between the outermost shell and the nucleus, and it can't really be measured directly. So in this diagram here, you can see that you find 2 bonded atoms, and you measure the distance from the nuclei, and then you halve it to get the radius. Very smart. Down groups, the atomic radius increases because the number of shells increases. So the outer shell will be further from the nucleus, and across periods, the atomic radius decreases because of the increased nuclear charge holding the electrons closer to the nucleus. You can see that in that graph up here, and then it shoots up and then goes down. Lower atomic radius means higher ionization energy because the electrons are closer to the nucleus. Now shielding is when the nuclear charge is partially blocked from the outer electrons by the inner electron shells. They absorb the majority of the charge because they're closer. This makes the outer electrons less attracted by the nuclear charge, therefore the ionization energy decreases. I like to imagine shielding as, imagine you're playing dodgeball and then people are throwing 100 balls at you, but if you're standing behind someone, then the person in front of you will take most of that, and then you'll be more safe than if you weren't standing behind someone. That's how I like to imagine it. The trend down the group. So down the group, the amount of shells increases, obviously, and then this decreases the first ionization energy because the larger atomic radius and shielding reduces the electrostatic force, or the attraction. So the nuclear charge increases, but the opposing factors counteract this, so it just makes it, So then there's a general trend in the first ionization energy. So I've circled the periods in red. Across the periods, the ionization energy generally increases because of the increased nuclear charge. When we go down the group, there's a sudden drop of energy, and we can use this to determine which period the atom's in. The atom with the low energy will be in period 1, and the periods will increase until the energy drops again for the next group. You can see that here. And you can see that there's smaller drops within periods, like it goes like up, down, up, down, up. and we'll look at that in a few topics' time. Or is that the next topic? Can't remember. General trend in successive ionization energies. In successive ionization energies, more electrons are removed from the same atom. The energy will increase because the ion will become more and more positive as you remove electrons, so that will pull the remaining electrons in closer. So this large jump in energy shows that an inner shell has been reached, causing the atomic radius to significantly decrease, which then increases the ionization energy. From this, you can tell that the atom here is in group 4 because there are 4 electrons in the outer shell. So these 4 are all in an outer shell, and you go up here, that's an inner shell. Summary questions. So 1, write the equation for second ionization energy. M plus, in the gaseous state, becomes M2 plus, also in the gaseous state, plus E minus. You've got to remember this, otherwise you lose a mark. How does first ionization energy change down the group? You put 3 points there. Down the group, the first ionization energy decreases because of the increased atomic radius and the shielding, and that counters the effects of the increased nuclear charge. Got to put that point in. And then 3, an element's first 5 successive ionization energies are 1,500, 2,300, 3,000, then 9,500, and 11,500. This is all in joules probably. What group is the element in? It's in group 3 because of the big jump there, that's an inner shell. So 7, electronic configuration. This is a horrible topic. So first, orbitals. Electrons are found in regions called orbitals, which can hold up to 2 electrons. The different orbitals are called s, p, d, and f. This is different from what we've learned in GCSE. An s orbital has the shape of a sphere that surrounds the atom, so you've got that nice sphere here and got the nucleus in the middle. So then the electrons can be anywhere in this sphere. Forgive my artistic skills, I can't draw with a mouse. But the electrons can just be anywhere on that sphere. And then a p orbital has the shape of a dumbbell, apparently. And there are 3 p orbitals along the x, y, and z axis, as shown in this lovely diagram. And each of these orbitals can hold up to 2 electrons. So it could be electron here. Maybe they're both here. That's just an area of probability, and that's about 95% accurate these orbitals are. And then there's the d and f orbitals. You don't need to know their shapes, but you need to know about them. You don't need to know their shapes because they're too complicated and it won't show up on the test. So subshells. Each shell has a principal quantum number n, which we looked at in the first topic, and then it will have n number of subshells, which refers to the orbitals. Shell 1 has the s subshell, shell 2 has the s and p subshells, so that's 2 subshells. Shell 3 has the s and p and d subshells, 3 subshells, and shell 4 has the s, p, d, and f subshells. And these subshells have orbitals, which add up to half of the maximum number of electrons in each shell. You can see the orbitals there. You can pause it to look at the graph, but this is the s subshells. They're all on separate shells. These are the p subshells. These are the d subshells. And then these are this is the f subshell. So that would be 1s, 2s, 3s, 4s, and then the same for the other letters. The periodic table. So now we're looking at it divided into blocks. So it's divided into blocks by which subshell their highest energy electron will be in. And for the s block, since there is one s orbital which can hold a maximum 2 electrons, group 1 and group 2 will have their highest energy electron be in the s block. Same for the other ones. These groups will have their highest energy electron in the p block, except not helium. Not sure why that's there on the diagram. And then, yeah, the same applies to the other blocks. And this is how you have to look at the periodic table for A-level chemistry. So here's the rules. The electrons in the orbitals must have opposite spins. Spin is just a property of particles. They're not actually spinning, I don't think. And these are represented by single-headed arrows pointing up and down like that and that. They have opposite spins. The subshells have different energy levels, and electrons will fill the lowest energy orbitals first, which is the Aufbau principle. Probably not pronounced that right, but you can see the energy. This is where the energy is on that diagram. And they'll also occupy empty orbitals before half-full ones of the same energy, because they're both electrons, they're going to repel each other, so they want to be far from each other, so they'll occupy the empty ones before the ones that have already got one in. Remember that orbitals can have a maximum of 2. So now we've got the electron in box notation. This is how you'd write out a cobalt, I think that is. So you can see the upwards pointing and downwards pointing arrows. And something to notice, the 4s subshell over here is below the 3s subshell. That's because it has lower energy than... That shouldn't be 3s, that should be 3d. It's lower than the 3d subshell because it's got lower energy. So the electrons will go into that orbital before doing the 3d orbitals, because Aufbau principle. So you can see the arrows here. It'll go 1s, 2s, 2p, 3s, 3p, 4s, and then 3d, and then 4p, and then all the other ones which we're not doing at the moment. So here's the electronic structure notation, which I think is also called the 1s notation. So I've got this here for comparison. Often you'll be asked to write this structure rather than the electron in box notation. So to do this, you only write the electrons in their subshells. You don't need to write about the orbitals. So here it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7. The superscripts up here are the amount of electrons in the subshell. It doesn't refer to what arrows are in the orbitals at all. The shorthand notation, since it's a pretty long notation, isn't it? So there's a shorter way. Since only electrons in the outer shell take part in the reactions, the inner shells don't really do much. You can write the electronic configuration in a shorter way using the noble gas that comes before it, since noble gases they're all full outer shells and they don't react. So this is that long notation that we saw on the previous page, and the short notation is Ar3d7 4s2. Since all this here, that's just argon, so you just write Ar3d7 4s2. These can be either way, it doesn't matter. The electronic configuration of argon is 1s2, I've already said that. So you can take this out of the configuration because these electrons, they won't take place in reactions. And then I've left the 3d7 subshell there because in transition metals in some reactions, the d subshell electrons can participate. Also because that's not part of argon. There's two exceptions or unexpected results. So there's two special elements, copper with 29 electrons and chromium 24 electrons. So think about it for a second. What do you think their electronic structures are going to be? Is probably what you said, if you've been paying attention. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9 for copper, and 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4 for chromium. That's probably what you said. But the actual is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. That's unusual. And then for that one, it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. That's also unusual. That's because the energy levels of subshells can move slightly, the amount of energy. And then having the 3D subshell half full or completely full is a lower energy arrangement than you would get by following the typical pattern. It's more stable. It's a lower energy arrangement because when I told my teacher it's more stable, he got a bit mad at that. But I think you can say that because it says that in the textbook. So for ions, the electronic structure changes because the number of electrons changes. And the ions are lost from the 4s subshell before the 3D subshell, despite it being lower in energy, because the 4s subshell is further away from the nucleus, like 3, 4. So experience less electrostatic force pulling it in, so the electrons are then easier to remove than those in the 3D subshell. So the example for iron is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6, and then you just get rid of that. It's for iron 2+, and then bam, it's the same except without 4s2. Summary questions. What is the electronic structure of sodium with 11 electrons? 1s2, 2s2, 2p6, 3s1, or Ar3s1. In the exam, you should put the long form notation if they don't ask you to put the short form notation. But here I'll let you off. So why are the electronic configurations of copper and chromium different from what is expected? Because the energy levels can move slightly, and having 3D subshell half full or completely full is a lower energy arrangement than what you would get by following the typical pattern. Question 3. What is the electronic structure of Fe3+ with 23 electrons? 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. There's no 4s subshell in there. Question 4. What is the electronic structure of Cl- with 18 electrons? 1s2, 2s2, 2p6, 3s2, 3p6. You'll see that's the same as argon, is it? No. One of the noble gases. 8. The last topic, and this is a really short one, periodicity. Periodicity refers to the trends and tendencies in the periodic table, and we've already done some examples of this, such as atomic radius decreasing across a period, or increasing down a group, trends in ionization energy, and elements in the same group having similar reactions. We've done a lot of this topic in mass spec, so I'm not going to go over how ionization energy covers it. But we will be covering how melting points and conductivity of metals are changing throughout the periodic table. So first, melting point. The first few elements in the period are metals, because that's the positive ones. They increase in melting point as you go across the period because there's more delocalized electrons and higher charges, so that increases the electrostatic attraction, increasing the melting point because you've got a break more forces, haven't you? And afterwards, the elements are covalent structures. Those are the non-metals. The first few covalent elements have high melting points because they are giant covalent lattices, and they've got huge amounts of strong covalent bonds to break. But then after that, there's simple covalent structures, simple molecules, where you have to overcome the weak intermolecular forces between them. And then the last element in any period is a noble gas, which is just a singular atom. It's going to have a very low melting point. It's actually called noble gas. Electrical conductivity. Across metals, the electrical conductivity increases because the charge becomes higher, and then the number of charge carriers, which is electrons, could also be ions, but not in this case, that increases, so the metal will be more conductive. In non-metals, the electrical conductivity is very low because the charge carriers aren't free to move. That's the electrons again in this case. And that's the end of that topic. Question 1. How does melting point change across period 3? For metals, it increases. For giant covalent compounds, it stays high, and then it decreases for simple molecular. Question 2. How does conductivity change across the periodic table? For metals, it increases, then it drops down for non-metals, because charge carriers. 3. Explain why the changes in the above questions happen. In metals, the melting point and conductivity increases because of the larger electrostatic force and more charge carriers. In non-metals, the melting point decreases because of the change in bonds, because metallic then covalent and just intermolecular forces, and the conductivity decreases because the charge carriers aren't free to move. And question 4, how and why does first ionization energy change across a period? We did that in subunit 6. You do 3 points for that. So point 1, across the period, the first ionization energy increases because of increased electrostatic force and lower atomic radius due to increased nuclear charge, and the number of shells is the same here, so there's no additional shielding effects. That's the end. I'm going to bed after this. Feel free to leave your questions in the comments. I'll try and answer all of them. I probably will answer all of them.